Hello everyone, this is day 3, problem 1 of our Leetcode activity. Given an array of integers nums which is sorted in ascending order, an integer target write a function to search target in nums. If target exists, then return its index, otherwise return -1. You must write an algorithm with O of log and runtime complexity. First of all, what is runtime complexity? A runtime complexity or time complexity is the number of elementary operations you need to perform relative to the input size. For example, we want to find the sum of first n natural numbers. We can also apply a for loop, a simple for loop which runs through, which starts at 1 and keeps on adding the next natural number until and unless you get to the number n. Now, think of it, how many times this for loop will run? It will run n times. So we can say that we performed approx n operations, n elementary operations for the input size n. But there is also a second approach which is directly using the mathematical formula. This is mathematical formula to find sum of first n natural numbers. So here, regardless of this number n, no matter how large the number n's value gets, we can always calculate the answer in just one operation, which is performing the mathematical calculation using the mathematical formula. So here we perform a constant number of operations, fixed number of operations for input size n. First we were performing n operations for input size n. Second we are performing constant number of operations for input size n. So this is time complexity, that the time complexity of for loop method is O of n, because relative to n we are performing n operations. Like input size n, we are performing n operations, and constant time complexity is regardless of the input size, we always perform constant number of operations. So similarly, there is n square, where you when it is mostly we see it when we nest loops, that the outside loop also runs from 0 to n. The inside loop also runs from 0 to n. So for when inside loop runs n times and also the outside loop runs n times, you can imagine the total operations will be n into n, which is n square. So here for input size n, we performed n square operations. So the time complexity is of n square. So this is what time complexity is. Now here it is said to do it in O of log n time complexity. So first of all, let us ignore this line and see, given an integer nums in ascending order, integer target, we have to find target in nums. If you want to find target in nums, the most simple or brute force approach we can think of is just iterate through the array one by one, check if that element is equal to target. If yes, return the index, and if no, return -1. Like we reached the end and we did not find our target, which means that element does not exist in this array. We return -1. But what is this runtime complexity of this approach? It is O of n. As in the worst case, the element does not exist, or it exists at the final or the last index, n minus 1th index. It exists at the last index. So we traverse the whole array. So for array size n, we should perform n operations. So the linear time, it is linear time complexity. Time complexity will be O of n. But here we are asked to do it in O of log n. So to perform this in log and logarithmic time, we need to apply the algorithm binary search. So pseudocode for binary search looks like this, but let us perform a dry run. I will explain binary search through this example. This is array, our input array, which has 16 elements and a target element which is 17. So we have to return the index where the value at that index is 17, and if 17 does not exist we have to return -1. First of all, we declare two pointers, low, high. You can also do left, right. There is no compulsion in naming. Then we set low to the 0th index, high to the n minus 1th index, which is the last index. Now we calculate mid, which is low plus high by 2. So 15 by 2 is 7. So our mid points to 7. So now does will check the value at mid. Does value at mid equal to our target? No. But is the value less than our target or more than our target or greater than our target? It is less than our target. So we simply bring our low to mid plus 1. Now why? First of all, we have to emphasize on the word sorted. Sorted is a really important term when we are thinking of binary search, because binary search can be applied to only and only sorted arrays. The array must be sorted if you want to use binary search. Why? So now mid, so we bring low mid plus 1. So now why do we do this? See, the target is 17. What we found was 15. So this guarantees that anything left of this index will be less than 17. Why? Because it must be less than 15, as this array is sorted in ascending order. And this is the importance of sorting the array or a sorted array, that we can say with guarantee that if the element at the mid is less than our target, anything left of that index will be less than our target, because this is a sorted array. So we bring our make our low to mid plus 1 index. This is mid plus 1, as anything to anything from this index to its left will be less than our target. So we simply bring our low to mid plus 1. Now again calculate mid, which is 15 plus 8 is 23. 23 by 2 will be 11.5. So we will bring it to our mid will bring to 11. So now, is the value at 11 equal to our target? No. Is it less or greater? So this is greater than 17. 23 is greater than 17. So we'll bring our mid, or we'll bring our high to mid minus 1. So now logic again is simple and straightforward. If this element is greater than our target element, from this element to anything right of this element will be greater than our target element, as this array is sorted in an ascending order. So we simply bring our high to mid minus 1. Now again we calculate mid, which is 10 plus 8, 18 by 2, 9. So we bring our mid to 9. Check, is 19 equal to our element, target element? No. 19 is greater than 17. So you simply bring our I to 8. Now you can see low and high are same. So mid should also point to the same element. And let us check, is the element at mid equal to our target? It is. So we have found our target element and we return the index 8. Now let us see if this was 18 and not 17. So now 18 will be more than our target element. It will be greater than our target element. So what do? We bring high to mid minus 1, and this is where we stop our binary search and say the element does not exist, as high has gone lower than the low, or the right pointer has gone left of the left pointer. So, and and the logic behind this is, just think of what are this low and what is this low, what is this high pointer. These are basically covering our search domain. Low and from low to high is our search domain, and we are trying to shrink this search domain down to that element. Like first of all, our search domain was the whole array. We calculated mid and accordingly moved our low to mid plus 1 or high to mid minus 1. So we halved the search domain. Again we halved the search domain. Again we halved the search domain until we found the element. But if the element does not exist, our either our high will go below low or our low will go above high. So in that case, our search domain has, what we can say, theoretically our search domain has gone to negative, as our search domain initially was high minus low. So if high gets below low or low gets above high, it has gone negative. So which basically means the element does not exist. So in pseudocode, a pseudocode for binary, we will write low equals 0, high equals nums dot length minus 1, while low is great less than equal to high. So this is our condition, that low must be less than equal to high. If high gets less than low or low gets more than high, we stop, as that is the condition we call that element does not exist in the array. We calculate mid. So this is a way to calculate mid to avoid overflow of value. So you can see high minus low by 2. So if you multiply here, so 2 low plus high minus low by 2. 2 low minus low is low, so high plus low by 2. So this formula rearranges to exactly how we calculate normally, which is high plus low by 2, but this is done to avoid overflow. So these are our conditions. If nums at mid is equal to target, directly return mid. Else if nums at mid is less than target, we bring our low mid plus 1. And if and it is not equal, it is not less, so that is greater. So we bring our high, mid minus 1. And if these all are performed and at the end low is not less than equal to high, so we stop this loop and just return minus 1, as the element does not exist in this array. Now how is this log time? We said na at the first that searching iterating through each element is n, because we are performing n operations, so that is O of n. So we are performing here log n operations. How? So think of it. Firstly, our search domain was 16 elements. Then, as mid was to 7, we took our low to 8. So we were down to 8 elements. Then 4 elements, 2 and 1. We are we keep on reducing our search domain by half, by 2 each time. So array size was n. Each iteration eliminates half of the remaining elements. So after each iteration, n by 2 element remain, n by 4. So after k operations, n by n by 2 raised to k elements remain. So ideally, at till what point we have to search till we find that one element, till only one element is remaining. So that is n by 2 raised to k should be equal to 1. So we can simply multiply 2 raised to k by to both sides. So n is equal to 2 raised to k, and take log 2 both sides. So that will be k is equal to log 2n. So what was k? K was iteration k. So basically k was number of operations. So number of operations are k, n is input size. So we have related number of operations to input size, and that is what time complexity is. For n elements, you need to perform k operations. And what is k? Log 2 of n, or simply log of n. And this is what the question was asking, to write a function of log of n runtime complexity, which we have done successfully here. So the C++ implementation of this is simple. We just declare low is equal to 0, high is equal to nums dot size minus 1, that is the last element, last index. Mid is equal to low plus high minus low by 2. If mid is equal to target, return mid. If less than target, we just simply bring low to mid plus 1. If it is greater than target, we bring high to mid minus 1. And if at the end we do not find the element, we just simply return minus 1. So this was binary search, basics of time complexity, derivation of why binary search is log n time, or what is logarithmic time. So in logarithmic time, any algorithm where you see that the elements remaining are always halved for each iteration, that is logarithmic time. That will be log n, because it will have similar derivation always, which is each time you are going on reducing it to half of the remaining. So at kth operation, it will be n by 2 raised to k, and we have to ideally go till only one element remains. So n by 2 raised to k equal to 1, n is equal to 2 raised to k. Take log both the sides, k is equal to log to n. So that is logarithmic type. And this is binary search. So binary search is much more than this. There are variety of binary search questions and variety of binary search approaches. We'll discuss them in future. This was just the basics. Thank you.